Can people hear me on Zoom? Maybe give me a thumbs up or something. Okay, I got one thumbs up on Zoom. That's great. Can I get a thumbs up from the audience? All right, got a few. Great. Well, thanks guys for coming to this electrochemistry crash course that we're going to be doing today. And thank you all for attending on Zoom. Electrochemistry is an entire field of chemistry, an entire subset. Let me see, I can't, when I go to the video, can people on Zoom, do you see the normal PowerPoint? I can't see the people on Zoom at the same time as I see the PowerPoint. So I'm switching back. Thumbs up, can you see it when I switch? Okay. So a little motivation, why would we do electrochemistry? Why bother at all? The one I think of first is energy storage. That's my particular interest with batteries, fuel cells, supercapacitors, other hybrid devices. But there's other applications as well. We can make microelectrodes that monitor neurons, very spatially specific. You can have them analyte specific, measure dopamine or other neurotransmitters emitted from a neuron. We could make devices such as sensors that are wearable, can be on the skin, could measure blood glucose levels or other analytes of interest. There's an emerging field of electro-organic synthesis where we use the electron equivalents driven to an electrode to drive reactions. And there's also the fundamental aspects of it, of electron transfer that we can study. We can measure diffusion coefficients through solution. Plenty of fundamental reasons why we might be interested in electrochemistry. So this course will be 3 days. We'll see how much I get through today. We have time left over. We're going to start on the second day. But today we're going to cover free energy of electrochemical reactions. We're going to look at a simple battery, and then we'll talk a little bit about electrochemical equilibrium. Everything I talk about today will be under equilibrium conditions. Next week, we'll get into electrokinetics. We'll study both Faradaic and non-Faradaic contributions to electrical current. We'll study various reversible reactions. We'll look at mass transport limitations, and then we'll look at some of the primary experiments that we have as electrochemists, including potential step, linear sweep, cyclic, voltammetry, and so on. Now, I will send out a doodle poll amongst the attendees for what topics we want to cover on the last day. Maybe it's something more practical, maybe it's something more obscure. I'll send out a list and we can vote on it, and the top 3 or 4 items that are chosen, I will present on, and we can kind of have a more open format on the last day. So moving forward.
Hi, Scott. Scott, we can't see the PowerPoint on Zoom.
You can't see the PowerPoint on Zoom. Okay. Can you see it now?
Now we can, yes. Thank you.
Okay. And on Zoom, you see the normal one?
We see what you see. So we see the next slide and the timing.
Okay, now you see the normal one, but my audience sees the other one.
Yeah, we see it a bit too big. It doesn't fully match. Like it's a little bit bigger than the Zoom screen.
Yeah, they're duplicated now. I thought they were before. When I enter slideshow mode, it gives me 2 screens. The fun of COVID times, guys.
Yeah, this is perfect. This is perfect. Now we just see the current slide, and it fills the screen, but it seems to match perfectly. Thank you. No, no. Now you undid it.
Yeah, so when I get it correct for the people on Zoom, it's not correct for the people in the audience present here.
Well, I guess this is fine. We can see your notes on the next slide, but besides from that, there's no problem because we see what you see basically.
Let's try one more thing. Okay, on Zoom, do you guys see the normal screen?
Yes, we see the current slide only.
Okay, all right, cool, we got it. We got
Thank
it.
you.
Okay. So, what determines if a reaction is spontaneous? This is an equation that we all know. It's the Gibbs free energy. It's the enthalpy and the entropy. And we know that a negative change in free energy, a negative delta G, is a spontaneous reaction. And so what determines if a redox reaction is spontaneous? If we have zinc 0 and copper 2 plus, and that goes to zinc 2 plus and copper 0, what determines if that reaction is spontaneous? That is this equation here, where the free energy is equal to the negative number of electrons times Faraday's constant times the voltage of the cell. And that's the standard potential of this E cell, and 1 mole per liter, standard temperature and pressure. So what is an electrochemical cell then? In the classic text by Bard and Faulkner, they define it as an electrochemical cell is most generally described as 2 conducting electrodes separated by an electrolyte. They don't define that it's a liquid or a solid. In fact, it can be either. So in this figure shown here, we have a zinc electrode separated from a copper electrode via a salt bridge. And so that makes it an electrochemical cell. And my computer's frozen. Give me one sec, guys. The computer's frozen. So if we examine this redox process, we have zinc being oxidized by 2 electrons and copper being reduced by 2 electrons. And we can split that into 2 half reactions. The oxidation of zinc plus 2 electrons and the reduction of copper plus 2 electrons. And then we have the summation shown here. And we're back and not frozen. And this cell potential is the energy in volts or joules per coulomb available to move external charge through an external circuit. So that would be electrons moving through this external circuit into the copper over here, reducing the copper 2 plus. So that's an external circuit to the electrochemical system. And the computer froze again. So practice and patience. Good. So what other important relationships can we make? We can derive this thermodynamic equation that relates the equilibrium constant with the standard potential. And we can make this away from standard conditions equation where the potential of the cell changes with the concentration of the various reactants. So if we change the concentration of zinc or copper, how would the potential of the cell change in response to that? And then another simplified equation that we can look at is the summation of the half reactions, where we take the standard potential of the cathode, subtract the standard potential of the anode, giving us the overall cell potential. And so let's build a battery. So if we look at this copper zinc system, we have the summation here of the E cell, and we know at the anode, and one tip for remembering the anode and the cathode is that generally oxidation occurs at the anode. So I think of anox and red cat. And if you look at a battery, the battery is always the red one, right? So when you jumpstart your car or anything like that, you have the red side and that's a plus. Red cat, anox. So we have an oxidation occurring at the anode and a reduction occurring at the cathode. And the overall cell is these two electron redox process. And it seems like most of the time I want to advance, it wants to freeze. Indeed, it is frozen again. So when we sum these two together, we will imagine, or we can go look up in a reference in a book, or we can even measure what the potential is versus some reference electrode, and see that for the oxidation of zinc, it occurs at minus 0.763 volts, and the reduction of copper occurs at plus 0.34 volts. And this is the shorthand for this reaction, where we have zinc reacting with zinc 2 plus in solution, separated by a salt bridge with aqueous 2 plus, copper 2 plus in solution, and then that is reacting with the copper metal. If we sum these two, if we take the cathode and we subtract the anode, we observe that this has a potential of plus 1.1 volts. So then I ask, is this spontaneous? And the answer is indeed yes, it is. If it's a positive electrochemical potential, then it has a negative delta G. So this is a spontaneous reaction, and so this would be a galvanic cell. So we often talk about specific reactions, and we often talk about them in terms of half reactions. And we can take advantage of this simple summation here, where we examine the E cell of as the cathode the anode subtracted from the cathode. But when we use a reference electrode, its potential does not change. And there are various reference electrodes that we can choose, the most famous being the normal hydrogen electrode, wherein hydrogen gas is bubbled into a solution at saturation, and it's in 1 mole per liter of H plus. And so that doesn't change. That potential will not change. And here are some other references. Silver chloride, you'll see very often. SCE, these are all done in aqueous solutions. In non-aqueous solutions, we typically see silver nitrate, and ferrocene is often used in situ. Now, when we use a 3-electrode setup, we have this reference electrode, and its potential does not change. So we can always reference the working electrode versus the reference. So we measure the cell voltage between the working and the reference electrode, and then we can report that against the chosen half reaction, our chosen reference electrode. So let's take an example of ferrocene. I mentioned that this is often used in non-aqueous systems. And remembering that we have that E equals the standard potential minus RT, that's the ideal gas constant, times the temperature, divided by the number of electrons times Faraday's constant, times the natural log of the ratio of the reduced to oxidized species. Now, by definition, E equals E0 when the concentration of the reduced species and the concentration of the oxidized species are equal to each other. Now, we often use the activity of these, but at low concentrations, they're going to be approximately equal. Sometimes in analytical situations, we do need to use activity and activity coefficient. For the purposes of this course, we're just going to consider the concentrations. So when these two are equal to each other, this value is 1, the natural log of 1 is 0. So these are by definition equal to one another. So if these values are not equal to each other, then the potential will change. So if we have a change in this value, then the measured potential will correspondingly change. Alternatively, if the potential of the solution changes, then the ratio of the reduced and oxidized species will change in correspondence with that. So then how does this actually change in solution? How do we map this out mathematically? So let's consider a solution of 5 millimoles per liter of ferrocene dissolved in acetonitrile with 0.2 moles per liter of lithium perchlorate as an electrolyte. Again, we have this relationship that I described earlier, and we can go look up the standard potential of ferrocene and see that it's plus 0.31 volts versus saturated Galán. And so we can rewrite this equation to put plus 0.31 in here, and it's the ferrocene versus ferrocenium ion. So we know at plus 0.31 volts, under equilibrium conditions, these two values will be equal to one another. So we might ask ourselves, what does this plot look like? At very negative potentials, it's intuitive to us that's going to be mostly in the iron 2+ state. At very oxidizing potentials, it's intuitive to us that it's going to be at the iron 3+ state. And since it's a natural log, what we end up seeing is these logarithmic sigmoids, where, again, at low potentials, let's say minus 0.5, it's mostly in the iron 2+ state. As you get closer and closer to the cell potential, to the standard potential, we see that the concentration of iron 2+ goes down and the concentration of iron 3+ goes up until they're equal to each other at 0.31 volts. And then it converts mostly to the iron 3+, very, very rapidly. Now, I like to make analogies to concepts we're more familiar with. So if we consider the redox processes and the equation shown here, the Nernst equation, if we compare that, well, first we can condense these variables here. We have RT over NF. If we're doing all of our experiments at room temperature, the ideal gas constant doesn't change, Faraday's constant does not change. We can condense these into 59 millivolts. And so that's very, very common to see in electrochemistry, that a lot of values will somehow be related to 59 millivolts. And if we look at the Henderson-Hasselbalch equation, we see that pH equals the pKa plus the log of A minus over HA. Now, in a lot of ways, this looks very similar here. We have the cell voltage equals the standard potential, and again, the peak where the standard potential is defined where A reduced is equal to A oxidized, and again, the pKa is defined where A minus equals HA. So they follow very similar curves. If we look at the oxidation and reduction of ferrocene, it follows a very similar shape to, let's say, the titration curve of acetic acid, or the speciation of acetic acid, where at low pH, it's primarily acetic acid. As you cross the pKa, it becomes primarily acetate. Now, we know that for every unit change in the pH, there's a factor of 10 change in the concentration. That's this log. It's a log base 10. I like to do an analysis or an analogy of the 59 millivolts here to one change in pH unit. So every time in a electrochemical potential we move 59 millivolts, the concentration changes by a factor of 10. So by the time we're up, 200 or 300 millivolts more positive or more negative than the standard potential, it's essentially all converted to the other, to the reduced or oxidized species. Something to keep in mind when you're doing, for example, cyclic voltammetry. So I have some homework questions for you all, and I'll send out an email. essentially aimed to calibrate you on these concepts. Now, I'm not going to collect the homework. I don't have time to grade it, but I will send out the answers. You can do this if you'd like. This is up to you. But I do think that it would be a valuable exercise to become more calibrated on these equations and the electrochemical equilibria. I also suggest the classic book, Electrochemical Methods by Bard and Folkman. Everyone who wants to do electrochemistry, I suggest you read the first 3 chapters and then decide after that what else you would like to study. Today I didn't talk very much about the derivation of any of these equations. I simply gave them out, but it would be valuable to go through those and go through some of the differential equations to derive those. I also recommend this ACS article, Beginner's Guide to Cyclic Voltammetry. They talk about some other electrochemical ideas in there as well. And then this recently published article, Potentially Confusing Potentials in Electrochemistry, where they help delineate electrochemical potential, chemical potential, electric potential, and so on. So I went through that quite fast. It's a crash course. So let's keep going. So we're in day 2. Hello, everybody. Welcome back. Today, and now we're going to talk about electrode kinetics, because the 2 things that govern whether a reaction occurs in chemistry are both thermodynamics and kinetics. If the thermodynamics are not there to drive the reaction, it will not occur. But simply because the thermodynamics are there does not necessarily mean the reaction will happen. The thermodynamically favored phase of carbon at room temperature is actually graphite. Diamond is not favored. So diamonds are not favored, and diamonds are not forever, but they're effectively forever because they're kinetically trapped. The energy barrier to conversion is too high, so that reaction does not occur. So diamonds are effectively forever. So let's consider when we place 3 electrodes in solution. The electrode has an energy level that initially is related to the work function of that metal, but it can be controlled externally using a device called a potentiostat, which will control the potential of the working electrode with respect to the reference electrode. And we'll get to the concept of counter electrode shortly. So when the energy of the electrode changes, it can cause current to flow between the electrode and the solution. So again, our thermodynamics are governed by this equation here. And if we imagine that our electrode is initially at some energy level here, and our species has a HOMO and LUMO gap of, let's say, 2 volts or so, and they're located at these locations versus the calomel electrode. If we change the potential of the working electrode, we'll eventually get to a level where it's higher in energy than the LUMO, and it will transfer an electron to the LUMO of a redox active species in solution. Alternatively, if we scan the potential in the opposite direction towards more positive potentials, eventually that will be at an energy level lower than the HOMO, and there will be an electron transfer from the species in solution to the electrode. And so electrons then flow to or from the electrode, and we measure that in coulombs per second, or amps. And so while that's traditionally done in a physics sense, we use coulombs per second, we can rewrite that such that it's electrons per second. And then if we know the surface area of the electrode, we kind of get an idea of how many electrons are transferred from a species in solution to the electrode. So there's a relationship between the current measured externally and the redox species in solution. And so when that electrochemical current flows to or from the solution, we call it Faradaic current. So there's a redox process happening in solution, and we call that Faradaic current. So as I mentioned earlier, the work function of the metal determines the energy level of the electrons in the metal. And when we control the voltage externally, we will see ions move in solution because they're charged particles interacting now with an electric field. So if we apply a more positive potential, anions from solution will migrate to be in close contact with the now positively polarized electrode. Alternatively, if we apply a more negative potential, positively charged cations will migrate towards the electrode to interact with the negatively polarized electrode. So when the ions adsorb to the surface of the electrode like this, they form what we call the electrical double layer, where there's the initial layer of, in this case, cations, and then you have another layer of anions just outside that. And these act like a capacitor because the charge flows and it's all confined to the surface, but there is no formal electron transfer to or from any species in the solution. And this current flow related to this double layer capacitance is deemed non-Faradaic current. So we have this non-Faradaic current that is not related to electron transfers to or from solution. And when an electrode acts in such a way that there is zero Faradaic charge transfer, we call that an ideal polarizable electrode. You'll often see that reference when electrochemists try to derive analytical solutions to electrode problems. And so that would look like something like this, where when you connect a battery, anions flow to one end of the capacitor, and then holes would flow to the other end of the capacitor. So let's examine some mass transport to the electrode. The electron, unlike a homogeneous solution, the electron has to transfer from a redox species in solution to the electrode at a very, very close interaction. It's not, and this is one area where electrochemistry can be very tricky, is it's not the same as if we had a stirring solution with a redox reaction occurring throughout the entirety of the solution. This is only occurring at the surface of the electrode. So in order to understand the electrode kinetics, we have to understand mass transport. That is, how do species from solution make it to the electrode and then do an electron transfer or do some sort of chemical reaction where we can observe that electrochemical current. So the first way is migration. So if we apply an electric field, charged particles will move in an electric field. We saw that earlier when I described the electrochemical double layer. However, if we use an electrolyte, as we often do in electrochemistry, that minimizes the contribution of your redox active species to migration. So the electrolyte will move, but our redox active species will not move through migration as much. The other way is convection. Typically in cyclic voltammetry, we do it on non-stirred solutions. But oftentimes it's advantageous to use a rotating electrode that's rotating at a very precise speed, and we know the viscosity of the solution, so we would know more or less what the flux of solution is to the electrode, giving us control over that parameter. And the last one is diffusion. And so diffusion follows Fick's laws, which we won't get into very much today, but as I know here, this is actually the primary limiting factor in of the redox active species to the electrode. So under non-stirred conditions, diffusion dominates our Faraday current. So let's consider an experiment, potential step voltammetry. So if we start with a 5 millimolar solution of ferrocene dissolved in acetonitrile, like we saw in the previous example, with lithium perchlorate electrolyte. We know that the standard potential is plus 0.31 volts. And again, we're reminded of this equation here. Our experiment looks something like this, where at some prior instance of time, we have an applied voltage of, let's say, 0 volts, and then we instantaneously jump to another voltage and stay at that voltage. So our perturbation looks like this. And so at 0 volts, we know that the primary species present in solution is the iron 2 species. Again, that's 300 millivolts more negative than the E0, so that's several orders of magnitude favoring the iron 2 plus state. Then if we jump to plus 1 volts, that heavily favors the formation of iron 3 plus. So when we do that jump, again, this is our perturbation, what will happen to our measured current? We like to make those predictions and then go do the measurement. So the first thing that we can think about is that ferrocene will be oxidized. So all of the ferrocene in contact with the surface of the electrode will begin to be oxidized. And then ferrocene from the solution will continue to diffuse towards the electrode, while the oxidized ferrocenium will diffuse away from the electrode. This is our Faraday current contribution. We will also observe that ions will migrate to charge the double layer for the non-Faraday contribution. So let's look at a mathematical analysis of this. So the ferrocene oxidation is diffusion controlled, and it's best fit assuming that the electrode is a infinite plane and there's semi-infinite linear diffusion to the planar electrode. And that's described here by the Cottrell equation, where we have number of electrons, Faraday's constant, area of the electrode, the initial concentration of ferrocene, the diffusion coefficient of ferrocene, and the time. Now you'll notice that the current is related to the inverse square root of time. So in my mind, anytime I see the square root of time in an equation, that's almost always diffusion. So and that's derived from Fick's law. So that's generally true. If a concentration is related to the square root of time, or you see any sort of gradient changing with the square root of time, that's generally related to diffusion. The non-Faradaic contributions, on the other hand, are best described using RC kinetics, where we have the solution resistance of the liquid and the capacitance of the double layer in farads. And you can see that this actually follows an exponential rather than a square root. And so if we look at the current versus time, and if you go do this experiment, you'll see an initial spike in the current, which will decay quite rapidly. We're looking here at about 0.5 milliseconds. And then it goes down to some smaller current value here. Now, if we look at the double layer charge, we see that it's higher than the Faraday current at the beginning, but then it actually decays faster. So the double layer charging decays much faster because it's exponential. The Faraday current doesn't decay quite as fast, and then at longer times, the Faraday current dominates. So in any potential step where we expect to see continued oxidation or reduction, when we do this experiment at very short time scales, we're probing the double layer capacitance, and at longer time scales, we would be probing the ion diffusion to the electrode. So I think that's a good place to stop for today. I know I went quite fast. I apologize for that. I hope some of that was clear. We still have plenty to cover for next week, but I don't want to saturate you guys too much. With that, can I answer any questions, or does anyone have any questions they'd like to ask? So an audience member asked, oftentimes she sees us in lab with stirring, and so depending on exactly what you want to probe, you may stir. So for example, if we're doing an electrocatalytic reaction, we want flux of species to the electrode. One thing that we should note is that we will not have a well-defined flux to solution if we use a stir bar. So I often use a stir bar in my experiments because I'm usually not limited by mass transport, and that's something we'll get into more next week. So if you're mass transport limited, you're limited by how quickly your reactive species can get to the solution, but that's not always the case. Other questions? Well, I'm going to make a couple of notes on the homework for the first week. So just thinking about how we would do this. So I'm mentioning that we're preparing a 50-50 mixture of ferrocene and ferrocenium. And if it's a 50-50 mixture, we know that it will necessarily be at the E0 to start. And so then I ask you, what is the E0 of this redox couple? So you can go look that up on your preferred reference. And then using the Nernst equation, calculate the amount of iron 3 at various potentials, and then calculate the amount of iron 2 at those same potentials. And noting that the total concentration should always be 5 millimolar. So something's wrong if it's not 5 millimolar the whole time. And then, like I showed earlier with these plots, I'd like you to make those plots so you can kind of have an idea of those mathematics and get calibrated on that. And then start to think about, here in this one, is iron 4 present? You know, we can measure the oxidation potentials of seemingly absurd oxidation states, maybe iron 4, iron 5, and then we can ask ourselves under what conditions does that exist? And even though it's logarithmic, and it smoothly decays, is there any of it present at these potentials that we're measuring? So I'll send this out in an email along with a doodle poll of what we will cover for the last day. Next week, we will continue with electrode kinetics, a few different types of experiments as well, including cyclic voltammetry, and we'll go from there. So if there's no other questions, I will plan on seeing you guys next week, and I'll send an email to everybody, and we'll see you next week. Thanks for coming.